Okay, so for this example, you can see it's the exact same problem we did before, except we're going to be solving this by the moment area method. As you can see, this is the cantilevered beam. It's a 4-inch nominal diameter standard weight steel pipe, projecting 12 foot from the fixed end. And what we want to do is calculate the maximum deflection at the free end. But this time we're going to do it by the moment area method. What we did up here, we did the same problem, but we did it by superposition using the formulas. So we're going to check our moment area method out on the same problem. Okay, so again, our moment of inertia is 6.82. I found that in Appendix B. And then our modulus of elasticity is 30 times 10 to the 6 psi, and that's for steel. Now the equation we're going to use here is y from A to B equals A sub m times x bar divided by EI. Okay, and that's the area, the moment area. Okay, so what we have here is the moment area, and then that's what this is here. This is the moment area right here. And because this line has two slopes, what we've done is we've divided the moment area up into 3 segments that we can easily calculate what the area is. So A1, this will be A1, is 1/2 of 1200, negative 1200, times 6. 6 is this length here. So the length times the height divided by 2 is the area. Okay, so that's 3,600 pounds foot squared. Area 2 is a rectangular area here. It's 1,200 times 6, or negative 7,200. I'm saying it's negative because it's below this line. Okay. A3, on the other hand, is again 6 feet. That's this distance from here to here. Times 2,400 pound inches, which is this distance right here, which is essentially 3,600 minus 1,200, and then times 6. So we have our 3 areas, and then so now what we have to do is find what our centroids of the areas are: x bar 1, x bar 2, and x bar 3. To find these, especially if we end up with a second-degree parabola and stuff like that, you're going to want to look in your textbook inside the inside cover at Table 2. So a right triangle, so we got 2 right triangles and a rectangle there. The centroid of the rectangle is easy. The right triangle, it's b divided by 3. So x bar for area 1 would be 2/3 of 6, or 4 feet. X bar of area 2 equals 6 to get from 0 to here, plus another 3 to get to here, to the centroid, so that's 9 feet. And then x bar for area 3 is 6 plus 2/3 of 6, or 10 feet. So we multiply the areas times the x bars, we sum them all together. In this case, they're all negative. And when I do this, I use the foot squared times feet. So there's cubic feet in the numerator here. And so in E and I use units of inch. But in these units here, I use feet. So I had to convert that. So I put this conversion factor in of 1728 cubic inches per cubic feet. And then I ended up with this negative number. Now the negative number is so that you know that's a negative deflection. Deflection is downward. By definition, deflection is downward is positive. So therefore I changed this positive to 1.277. So anyways, what happens here is we went through this moment area method on this problem, and we've got the same answer within 1,000th of when we did the problem by the formula method by parts, by superposition, I mean. So that is example 1510. The last one I want to talk about now is 1514. Calculate the deflection at midspan for the beam shown. The beam is a nominal 4-inch diameter standard weight pipe. Again, neglect the weight of the beam. So this one's going to be complicated in terms of finding the areas. So what we want to do is draw the moment areas by parts. Okay, we're going to consider the moments about this point B here, in which case we've got 1, 2, 3 forces causing moments about B. Okay, so the first one, the reaction at A. That reaction A is 1,100 pounds. Multiply it by 10 feet. I get 11,000 pound-feet. Okay, and it starts at 0 here, and it goes up to that point. And that's positive because A is pushing upwards. Now, this load here of 1,800 pounds is pushing downward. And it starts at the point load at 0, and by the time it comes to point B, it's 1,800 times 5, which is 9,000 pound-foot squared. And then finally we get this 800 here. That's 800 times 2.5 feet is 2,000 here, and that's how we get that. So what are these areas? Okay, so delta C is the deflection midspan. Okay, so what we want to do here is find A1, which is 55,000 pound-foot squared. Okay, so that's this area here, which is 1/2 of 1,100 times 10. Area 2 again is 1/2 times 9,000 times 5. And then A3 down here is 1/2 times 2,000 times 2.5. And then I need to find what my X bars are. Okay, so again, these are centroids of triangles, and so that's like third, B over 3. So therefore, YBA is A sub M times X bar over EI. I do that equation, and then what I get is this 1.241 deflection, YBA. Then what we're going to do is find this YC by proportion, similar triangles. Okay, because this is the YBA, okay, and then this is the YC. Now please note that this is not our deflection. The YC is the distance from the unbent beam to the point where this tangent line intersects the beam at point C. That's what YC is. Really, the deflection here is this delta C. Okay, so what we have to do is we have to do this two different ways. We have to calculate what YCA is first, and again, it's the same way: A sub M X over EI, and I get 0.194 inches, and then I subtract that from 0.607, and I get 0.413.